Welcome. In this video, we'll continue our discussion of chemical bonding. In this video, we'll focus on metallic bonding. Metallic bonding is a special kind of bonding that occurs between metal atoms. And it's different than ionic bonding. And it's also different than covalent bonding. It's a special type of interaction between atoms. So in metallic bonding, we're going to have electrostatic interaction or attraction that occurs between our positively charged atomic nuclei, where we have our protons, and the free moving valence electrons in the metal. So during metallic bonding, our valence electrons are going to be in constant motion, moving from one atom to another. These electrons that are moving around are not associated with any specific atom, but they move freely throughout the metallic substance. So the electrons are moving from one atom to another, which is kind of like ionic bonding, but they're also being shared in between the nuclei, which is kind of like covalent bonding. But they're never ever on one specific atom for very long of a time. And we consider these electrons to be delocalized or non-localized because they're moving constantly in between all of the metallic atoms have few valence electrons and they tend to have low ionization energies. That means they're not really able to achieve a noble gas configuration by adding electrons onto themselves in a traditional covalent or ionic bonding. So we have to do this special type of metallic bonding where electrons are sort of all moving around in between our nuclei. So we can think of this as our atoms of metals being in a fixed crystal arrangement, and they achieve the more stable electron arrangement by sharing their valence electrons among themselves in a mobile sea of electrons. So we have this mobile bunch of electrons floating around and our nuclei are in the middle, and by having this flux of electrons moving through the metal atoms, they're able to achieve stability and get closer to an octet. So the electrons do not belong to individual atoms, but rather to the metallic crystal as a whole. So this is a nice graphic here where we have our nucleus of an iron atom, and we have the valence electrons floating around in this sea of electrons. So those electrons are being shared between all of the nuclei in here, moving around all over the place, and getting our atoms to a more stable electron configuration. It's not a full loss or gain, and it's also not a full share, so it's its own special type of bonding. And we see this metallic bonding in solid metals like copper, iron, and aluminum. And we typically find metals as solids at standard temperature and pressure. Because those bonds are strong, they hold the atoms together in a solid phase. There, of course, are some exceptions to this rule. Mercury is going to be liquid at room temperature, and gallium has a very low melting point compared to other metals. The physical properties of our metallic elements are luster, they're very shiny, conductivity, so they're able to conduct electricity, which is just more electrons, which makes sense because we can get more electrons through that sea of electrons quite easily. Also, they're malleable, so we can change the shape of our metals pretty easily. Because they don't have well-defined bonds and just that sea of electrons, we can really change the shape quite easily. Ductility just means that we can stretch them into wires, and they tend to have generally pretty high melting point, so we have to really heat these guys up to get that sea of electrons to disperse. So we have a couple of practice problems here. Which statement best describes the type of bonding that exists in a sample of solid titanium metal? So whenever we're talking about solid titanium metal, our metallic bonding should come to mind, right? Metals, if it's just the metal atoms with no other element attached, we're not going to have covalent bonding. We're not going to have hydrogen bonding. Dispersion factors are not what's happening here, but our metallic bonding is what's going to be contributing to the bonding in a titanium metal sample. And then our next question, which substance contains metallic bonding? Here we get out the periodic table and look for a metal on the periodic table. Phosphorus is a nonmetal. Iodine is a nonmetal. Germanium is a metalloid, and thallium is our metal here in this list. So if we find thallium, which has a symbol of Tl on the periodic table, we can see that it's a metal, and that's going to be involved in metallic bonding. Okay, that does it for metallic bonding. These are bonds that are going to happen in between metal atoms. The metal atoms are going to share their electrons in a sea of electrons surrounding our positive nuclei. This is going to make them have very strong bonds. It's going to allow for the physical properties of metals that we see, like good conductivity and high melting points and malleability, because of those types of bonds. And we can recognize that something has a metallic bond by looking for a metal only in our compound. Go to work today. See you next time.